algorithms how to analyze the protein-ligand interaction. And we were already talking about the protein-protein interaction. This is the protein-ligand interaction. Now, of course, I'm kind of envious, you know. I'm envious because this guy got almost 50,000. I wanted to do something like that. So for that, I'm not really good enough. So I have like 44,000, these like 10 times more. So this is just a joke, of course. Don't take it seriously. Yeah. So this is the idea, because he developed the algorithm at the US. Scripps Research Institute. This is the top institute, private institution in the United States. Probably, I'm not sure whether you know this Autodoc, Vina and Autodoc, which is the golden standard for the protein-ligand interaction. Everybody's using it. You got hundreds, thousands of citations. He just got this for one paper. And right now we are working together to come up with the idea how we actually improve this particular algorithm. Because the problem is when you do the interaction, when you do the protein-ligand interaction, you got the difference between different iterations. You will, for instance, you will do 3 times, you will do 5 times, and when you calculate the standard deviation, it will give you the affinity change in the Gibbs free energy of binding from 1 to 2 kilocalories per mole. This is tremendous, because if you will convert it to the KD, the dissociation constant, then it will give you because it's logarithmic, it will give you the orders of magnitude change. So once you got the 1 kilocalories per mole difference in the experiments, you got in affinity in IC50, you might have a difference from 10 to 100 or even 1,000. So it's kind of unreliable. Therefore, we came up with some strategy and how to let's say, bypass this particular drawback. And as you can see, the idea is just to calculate some kind of S-like curve. And the S-like curve will calculate the transition Gibbs free energy of binding at some sort of IC50. Of course, in pharmacology and the standard curve for the pharmacodynamics is the S curve, the dose response curve when you have IC50. Here also reminiscent this kind of curve, and then you can just simply calculate the transition state, and you see this transition state is very precise. So when you got the difference, you will have in terms of the 1 to kilocalories per mole, and once you calculate the transition state, it's always the same. The only thing is you can probably calculate it in a more robust way, so you will increase the correlation coefficient. So this is to make you just do it much faster, yeah? Because this is for 40 iteration. If you will increase it 2 times, then you also improve the correlation coefficient. So, and this is the project is going to be published together with Professor Trout from the US. Okay, this is the other project. I'm just trying to give you the idea of what we are doing. This is the parasitology, and this is the trypanosome. The trypanosome is probably, I'm not sure whether you're working here with this particular parasite, because it comes from Africa, and it causes the sleeping sickness in Africa, and particular trypanosome brucei. And this particular trypanosome has a very peculiar mechanism how to evade the attack of the immune system. And on the surface of this parasite, you have some proteins. They're called BSG proteins, glycoproteins, and it is well known. It's very kind of complicated protein. Has different domains, also some anchors. It can be attached to the membrane, and on the surface of the parasite. And once you get the antibody-antigen interaction with the parasite, it can be internalized by parasites and then processed and just got nothing will be exposed on the surface of the parasite, and there is no any immune response is triggered by the particular antibodies on the surface of the parasite. So this is very peculiar mechanism of the defense. And as you can see, it's also quite mobile because we also trying to investigate the computational fluid dynamics using this parasite and how this parasite behaves when you simulate in the bloodstream, for instance, because it also has the flagella, and the parasite could also redistribute this particular proteins to the flagellar part of the body, and then it can be internalized. And so we think that the idea is what's going to happen with the protein protein interaction, like antigen-antibody complexes, when you will internalize this particular complex, and what will happen in the lysosomes, because in the lysosomes you have low pH, because it is well known some parasites and viruses, they are using kind of conformational shift in the proteins, and it is triggered by the different pH. I mean, is it okay with time? Is it fine, right? Because you have to tell me where I can stop, because I can just talk for 2 hours, 3 hours, 5 hours.
5 minutes.
5 minutes? Okay, good. And to make story short, we analyze the protein conformational shift using different spectroscopy. This is the size exclusion spectroscopy, and we have found that you have a minor shift in different pH. I was also using Monte Carlo here just to investigate the energy, and we were trying to investigate the different epitopes on the surface of this particular protein. And when protein is exposed to the exterior, the epitopes are also exposed, and vice versa. If the protein is kind of more closed, then the epitopes are less exposed. And we think this might be also the very important mechanism, might be very important for the formation of the antigen-antibody complex. Okay, this is about chemistry. We're trying to do some biomimetics materials, which are very important, for instance, to treat some diseases like osteomyelitis. We have hydroxyapatite. On the surface, we will put some substances like antibiotics, quercetin and tetracycline, and we see what is happening with the attachment and how we can improve attachment using different also modeling here. This is the membrane with different hydroxyapatite molecules, and we are also developing some therapies against infectious diseases like bone infectious disease. And here's the microscopy, atomic force microscopy, some elemental analysis. I'm not going into detail, but we actually quite proficient in different chemical evaluation techniques. This is UVs. I'm also supervising a lot of students on the chemical characterization of substances, like different spectroscopic techniques, and so on. And just a couple of words about the future plans, what we have. Of course, we have also the virtual reality lab. This is my student trying to figure that out, what is happening with the drug within the protein, and we are also working on the algorithms. And some robotics facilities. This is the lab we have, and QCA, the robotic arm, so we can actually program it to do the drug design. I already explained to you. For instance, we can improve the AI model for the blood-brain barrier research here. And this is the quantum computer in Germany. I'm also kind of interested a little bit in quantum computing. So I'm trying to reverse the chemoinformatics algorithm, kind of develop, let's say, chemoinformatics algorithms using the quantum computing machinery. And here we have the quantum computer in Germany, in Jülich. So hopefully there will be also very interesting projects in the future. And from Prof robotics, as I was talking about previously, where we have a lot of robotics, we can actually roboticize the in vitro systems we have now, which are kind of laborious. Okay. And this is all. Thank you for your attention, and I'm looking forward to any questions from you. Thank you.